Alright, so in this tutorial we're going to summarize the key factors that affect the force of friction as something slides across the ground. We're going to introduce a new equation. It's an important equation, one you developed from your lab. It might be helpful to have your reference tables in front of you, because I'm going to point out a table there that is going to be relevant for some of the problems. If you don't have it, we'll bring it up in class. But if you want to pause now and go fetch it, I would do so. Alright, so we're going to start off by reviewing what are the key graph from the lab, and that is looking at how the force of friction changes or varies with the normal force. Okay, we choose the normal force because you can change the normal force without adding or subtracting weight. There are ways of doing that. We'll talk about that in class. Generally, the normal force is going to be equal to the weight of the object, but that's not always going to be the case. However, the force of friction always depends on the normal force, and the normal force can change even if the weight doesn't. So that'll become clear later on. All right, so we have two graphs. One is showing sandpaper is being slid across the surface with different normal forces, and then the one is wood. We notice that both have a straight line. So a very important relationship is we can see that friction is directly proportional to the normal force. Okay, and that's nice and simple. One way to look at that is if you double the amount of friction that's acting on a car that's trying to stop, then you're going to double. I should say the normal force is going to double the frictional force. Okay. So that doesn't necessarily mean it's going to double how fast you're going or slow you down in terms of the velocity. It just means that if you double how much weight you put in your car, you're going to have that much more friction. Okay, and as I said earlier, usually one changes normal force by adding or subtracting weight. Okay, but there are other ways of doing that that we'll investigate. So we want to look at this a little bit further, because we have a straight line. We can make equations from straight lines, and so we want to understand the slope. And the reason that the sandpaper has a much steeper slope than the wood, even though they both change friction with normal forces, there's something different about them, and that's really differences in surface texture, not surface area. We'll address that later, but how rough or smooth the surface is. So sandpaper is generally rougher than wood, so for a given normal force on a surface, we'd expect to be more friction with sandpaper than wood. If we were to change it to, let's say, wax or ice, then we would see that the friction grows very, very slowly with weight. Okay? So we don't expect different surfaces to have the exact same lines. We expect them to be lines, but with different slopes. So the slope tells us something about the surface texture. Okay? And so when we go to find a slope, and we're indirectly using that to indicate the surface texture, we want to give it a name. So the slope represents what we call the coefficient. Coefficient is just a fancy way of saying a number of friction. Okay, and it is given a symbol, the Greek letter mu. Okay, it looks like a mu with a little tail on it. So when we go to do a slope of the sandpaper, we're really doing the change in force of friction divided by the change in the normal force. And what we'd get, let's say this was the change in normal friction for that part was 10 newtons, and let's say for this one it was 20 newtons. What we do is then our coefficient would be 10 newtons divided by 20 newtons, which is 0.5. And what you want to understand is the newtons cancel out. So there are no units associated with the coefficient of friction. However, it is something that is based on a physical property. Okay, so how do we interpret coefficients of friction? Well, pretty straightforward. The higher the coefficient of friction, the rougher the surface, and therefore the greater the amount of kinetic friction. Okay, again, that's assuming you have a constant normal force. So if you have a certain amount of weight that's sliding across a slick floor versus a rough floor, the rough floor has a higher coefficient, therefore greater force of friction. All right, now generally you can get mu, the coefficient of friction, from the slope of a graph, or we can look it up on the front page of a reference table. So that's why I have it out. If you go to the front bottom right, you'll see something says approximate coefficient of frictions for various surfaces. Rubber on concrete or asphalt, like tires on a road, ski and or ice and snow, and then even wood, steel, and Teflon. So we'll say more about that in class. Anyway, the graph above leads to a very important equation. Okay, we have again force of friction, normal force, and a straight line where the slope is the coefficient. So we can say that y equals m, the coefficient, times x, the normal force. And we call that the fun equation, F-U-N, or you could call it fuffin, as someone generally, some people like. All right, so it's a really nice equation. So if you are told something about the surface, and you're told about how much normal force is pressing onto the surface, then you can predict or calculate how much friction there will be. Okay, and the normal force is usually equal to the gravitational force, and the gravitational force is always equal to the mass of the object times the acceleration due to gravity. Okay, so if we have a situation where we're trying to slide something across the ground, we're putting an applied force here, and we're asked to find the force of friction that might be opposing it, okay, we'd have to know something about the surfaces to get the mu part, and then we could, if we know the mass, we could say the normal force is going to be equal to mg in this particular case, because the normal force is being balanced by the gravitational force. If there were other downward forces, then the normal force would be different than the weight, and we'll handle that when it comes along. Okay, so a simple little problem. A 3 kilogram block of wood slides across a wooden surface and at a constant speed. So how much kinetic friction is opposing the motion? Well, if we do a force diagram, we want to make sure we got all our forces in the world. We must be applying a force, because if there's friction and we're moving at a constant speed, these two must be equal to each other. So in the horizontal direction, the applied force equals the force of friction. Okay? So if we want the force of friction, we would say the coefficient of friction times the normal force. All right, now where we need the coefficient, it wasn't given, but the fact that we have wood on wood, if you go to your reference tables, and if you don't have in front of you, take our word for it, we see that the coefficient for wood on wood is 0.3, and that's for kinetic. If it was static friction, it would be something else. And then we got to multiply it by the normal force, and from our force diagram, it should be pretty clear that the normal force is balanced by the weight. So that's going to be, the normal force is m times g, okay, which is going to be about a little less than 30 newtons if I call g 10. So if I do 0.3 times 30 newtons, okay, I see that the force of friction is 3 times 3, 9 newtons. Okay, so that's really the simplest way that you can use the fun equation. All right, let's move on. So one might ask, and you ask a lot of people, well, what other factors affect the force of friction? And very often you hear surface area. Okay, not surface texture, but the area. How much of the block is in contact? So in this situation, let's say we have 2 blocks of wood. Here we have a very large surface area in contact, and here we have a small surface area. Okay, so common sense would suggest the greater the surface area, it has a greater friction, and that would be wrong. Okay, so common sense, once again, is not true. So in other words, surface area plays no role. 2 ways you can try to look at that if you want to understand it. All right, any increase in surface contact, let's say in this guy right here, is offset by a proportional decrease in pressure. Now we really haven't formally talked about pressure, but essentially what's happening is, even though this flat one is covering more, touching more area, the weight of it is distributed over a greater area, and that cancels out the area effect. Whereas this guy is touching a small area, but its weight is distributed over a much smaller area, concentrated, so it offsets it. Another way of looking at it is, regardless of which face is in contact with surface area, with the surface, the normal force is the same, right? In both these cases, it's the same normal force acting on them, and the coefficient is the same, because coefficient depends on what? Think about it. What does the coefficient depend on? That's right, the texture. And friction. Doesn't matter how much or how little is touching the surface, it's the same roughness or smoothness. Okay, so that's an important point that you'll be asked about. Surface area, it has no role. Okay, lastly, from the lab, is more force needed to start an object moving than to slide it across the floor? Okay, so what we're really talking about is static friction versus sliding friction. In other words, how does static friction needed to get a block starting, that's the definition of it, compare to sliding friction, which is needed just to move it along a surface? From your data, it should have been pretty clear, especially as the weights kept going up and up, is that static friction is always greater than sliding friction, which means you need more force to get something started than to just slide it along. So if I've got a block sitting on wood here, let's go back to our previous problem. Whoops. Okay, where we had this here, we were calculating kinetic friction. So we had 9 newtons. Well, if this block stopped and we were on the same surface, we try to pull it again, then we'd expect a greater than 9 newtons to get it started. Okay, so it might be 10, it might be 15 newtons, and what we'll see in our reference tables is that there is a coefficient for static friction. In other words, the coefficient for getting it started versus sliding it, which has a slightly less value. All right, so let's finish up with some questions. In the wintertime, what are 2 things you can change about your car or truck to increase the amount of friction? Okay, the obvious thing is to, well, maybe it's not so obvious. The common thing is to add weight. Okay, adding weight can give you more friction because you know friction is proportional to normal force. And more normal force is more weight. The other thing you can do is do something about your tires. Maybe get, we'll say tires. Get snow tires, make sure they're not bald. Sometimes people put chains on them. What you're essentially doing is affecting the coefficient of friction. All right, number 2, when you roll to a stop, what stops you is static friction. Okay, when you slam on the brakes and skid, it is kinetic friction that stops you. Okay, so based on your answer above, why is it better to roll to a stop than skid to a stop? Well, this requires static friction, so I'm going to call it force of friction static. This requires force of friction kinetic, and we learned that static is always greater than sliding. So when you have static stopping you, you're not going to roll as far as when you're skidding. When you skid, you're going to go further, which is more likely to hit something. So that's why we've developed anti-lock brake systems, so your car is less likely to skid when you slam on the brakes. And lastly, if your wheels are slipping on snow as you try to go up a hill, why will letting some air out of the tires help your traction? My uncle told me this many years ago. I've never seen it, but I took his word for it. I thought it was surface area, but that I knew surface area doesn't matter. But what I didn't realize, and then looked up, is that less air in your tires makes your rubber tires softer. So why would that matter? Softer goes towards texture, and texture is really measured by the coefficient of friction. So if your tires are overinflated, they might be a slightly different consistency, if you will, than underinflated, and underinflated give you better grip. And better grip is going to allow you to not slip as much. Okay, so we'll do some practice in class with this, but hopefully you see this is a pretty straightforward concept.